Hello and welcome back to Nunley Math. Thank you so much for joining us here today as we begin a brand new unit on linear equations. Linear equations. We've spent the last couple units talking about probability and some geometry, and so I'm excited to wrap this all back around and tie it into a little bit of Algebra 1. So without further ado, I want you to check this problem out. I want you to create an algebraic model for a scenario and solve. Jillian's new puppy loves to chew things. Aw, isn't that cute? He finds his way into her room and discovers her secret stash of gummy bears. He eats 12 gummies right away and then knocks the bag onto the floor. He then continues to eat about 3 gummies per second. How many gummies does he eat? Now you'll recognize this as being an application problem like we might have seen during our earlier algebra units. And when we would solve an application problem, we said the first thing you always have to make sure you do is define your variables. Then write an equation using those variables, solve that equation, and use your solution to give your answer, always as a sentence. So I'd like you to pause the video, take just a second, see if you can figure out how many gummies the puppy eats. I am going to go ahead and continue on and work this out, assuming you have already done that on your own. Hopefully, when you began to think about the solution to this, you realized that there's a problem with the question, and that is the amount that Jillian's puppy eats is dependent on how much time he has to eat. It is impossible for us to just look at this problem and know how many gummies the puppy has eaten because it says he eats 3 gummies per second. Depending on how many seconds have passed, our answer is going to change. The amount he eats is dependent on how much time he has to eat. And without knowing how much time has passed, it's impossible to know how much he has eaten. There are many, many possible solutions to this particular problem. So here's what I'd like us to do. I'd like us to take a look at some of the possible solutions that occur in this particular story. For example, if we can stop the puppy after 0 seconds, the minute those gummies hit the floor, we know that we still will have a puppy with 12 gummies in his belly because it says he ate those right away. But as time passes, the problem tells us that he's eating more and more gummies. He eats about 3 every second. So after 1 second passes, we have those 12 gummies he originally ate plus 3 more. And another second passes, now we're at 18. And another second passes, and another second passes, and another second passes. And hopefully, you notice that the pattern is occurring where we are growing by 3 gummies every time. Now, we've just illustrated what was told to us in the problem. Our rate of growth is 3 gummies per second. 3 gummies per second. Let's think about this for just a moment. If 0 seconds have passed, we have the 12 gummies we originally ate, and those 12 gummies stay with us no matter how much time passes. They are constant. But if only 0 seconds have passed, we do not add any additional gummies to those 12. If 1 second passes, we have the 12 that we ate instantly, and we have 3 extra gummies in that 1 second. And if 2 seconds pass, you'll notice that we have the 12 gummies we originally ate, and we have 3 gummies twice, once for the first second, once for the second second. And after 3 seconds, we have the original 12 and 3 sets of 3, and the original 12 and 4 sets of 3, and the original 12 and 5 sets of 3. This pattern is going to be consistent no matter how many seconds pass. You will always have the 12 gummies you originally ate, or the puppy originally ate, but we need to keep track of how many 3s we need to add on. So I could say, for X seconds, or any number of seconds, when I look at the pattern, I can see right here that I'm repeatedly adding a 3. Remember, repeated addition is just multiplication. So I have no 3s, 1 3, 2 3s, 3 3s, 4 3s, 5 3s. And the number of 3s that I have is the same as the number of seconds. So in 5 seconds, I have 5 sets of 3. So it's always 3 times the number of seconds. But don't forget, no matter how many seconds pass, we always have that plus 12 at the end. This pattern right here can be used to calculate the number of gummies that are eaten. You have an original 12, and then you have however many threes, and that number of threes is going to match the number of seconds. Does that make sense? The pattern allows us to predict for any amount of time, that's the independent variable, how many gummies your puppy has eaten. The gummies depends on how much time has passed. So, if I were to ask you how many gummies can he eat in 1 minute, well, we always start off by rewriting the original pattern we're working with. This is gummies equals 3 times the number of seconds plus 12. And then we just substitute in for what time we're looking for. Since my time is in seconds, I'm going to plug in 60. Remember, 60 seconds is 1 minute. So he has his original 12 that he gobbled up right away, and in 60 seconds, he's going to eat 60 sets of 3 gummies, or 180 gummies for a total of 192. We always rewrite, substitute, and simplify. And that's how we can work with scenarios with only, or where we're missing a piece of information, or where we're given a relationship but a value that we need is unknown. These are called linear equations. Linear equations always have this constant rate of change. Does that make sense? I got a couple more examples of this I want you to try. Take a look at this one. Notice that Liam interrupts Mr. Nunley about 6 times every minute. If we assume that Liam has already interrupted Mr. Nunley 30 times before we start timing him, give a function that allows us to find the number of interruptions over time. The number of interruptions over time. So I have 2 things here I'm talking about. I'm talking about how much time has passed, and I'm talking about how many times I have been interrupted. One of those is dependent on the other. Do the number of interruptions depend on how much time has passed, or does the amount of time that's passed depend on how many times I was interrupted? Well, hopefully you realize we don't control time. Time passes independent of our decisions. But the interruptions that we have depends on how much time has passed. So if I were to come over here and I wanted to write out for you what my independent variable was, I would say my independent variable is time in what we're using minutes, I believe. Yeah, it says minutes. It's the time in minutes. And we're going to represent that with the variable x. The independent variable is always represented by x. The interruptions, though, are going to be my dependent variable, because how many times I've been interrupted depends on how much time we give Liam. So let's say interruptions. It's hard to write with a mouse. Interruptions. I should get a cool stylus like some other YouTubers have. That'd be cool. There we go. So my interruptions are going to be the dependent variable. Notice that I've switched from using y to using f of x. It really doesn't make a difference. Mathematicians use both versions, so you'll see me switch back and forth to get you used to that. Just know that they mean the exact same thing. When I use y, I typically refer to linear equations. When I use f of x, I typically refer to linear functions, but they both mean the exact same thing. Well, let's create a table to look at this scenario. If 0 minutes have passed, Mr. Nunley has already been interrupted 30 times, so he has no time to interrupt me anymore. But if we give Liam a minute, he'll interrupt me 6 more times for 36. And if you give him another minute, he'll interrupt me 6 more times, and another minute he'll interrupt me 6 more times, and another minute he'll interrupt me 6 more times, and another minute he'll interrupt me 6 more times. In fact, the pattern that's described for us is about 6 times every minute. And so you can see that our constant rate of growth is plus 6. That means that no matter how much time passes, we'll always have those original 30 interruptions. But as time passes, we're going to keep track of how many sets of 6 we're adding on. So if 0 seconds pass, we have the original 30 and no more interruptions. If we have 1 minute that passes, we'll have the original 30 interruptions plus one set of 6 more. And in 2 minutes, we'll have the original 30 and 2 sets of 6, and the original 30 and 3 sets of 6, and the original 30 and 4 sets of 6, and the original 30 and 5 sets of 6. No matter what number of seconds pass, we always have groups of 6 interruptions. The only thing that changes is how many sets of 6 we have. It's going to be the same as the number of minutes, 6 every minute. 6 every minute, 6 every minute. So this is 6 every minute. And don't forget, we always have those 30 extra interruptions from before we started timing. That is going to be our function. 6x plus 30 equals f of x. Now, if I wanted to know how many times Liam would interrupt Mr. Nunley in a 52-minute class period, just like in the last example, I'm going to take that pattern, that f of x equals 6x plus 30, and I'm just going to plug in 52 minutes. In 52 minutes, he will interrupt me 52 sets of 6, plus the 30 we already had, or 312 plus 30, which is 342 interruptions. Get the idea? Couple ideas here we want to make sure we're clear on. What's the difference between independent and dependent? How we find that constant rate of change, and then how we can use the table to find our pattern. Once you know the pattern, you can plug it in and solve. Here's what I would suggest to you. I would suggest taking just a couple minutes and trying this next one on your own. Sometimes it's easy to assume you understand when I'm telling you how to do it the whole way through. It's like, oh yeah, that makes sense. But to be able to recall and duplicate it on your own is a very important skill. So I'm going to highly suggest you do that. Obviously, if you get stuck, you're going to want to start the video and work your way through it, maybe pausing when you think you understand again. I'm going to go ahead and assume that you've done that if you wanted to, and I'm going to keep going. Charlotte and Lydia are canoeing down the river. They've paddled for 23 miles already when they decide to stop and let the 2-mile-per-hour current carry them down the stream. What is the total distance they traveled? Two things we're working with here. Number one, we're asked about the total distance, but we're not given the total distance. What we're told is they've gone 23 and the current is moving 2 miles every hour. But we don't know how many hours have passed. We need to set up an independent and a dependent variable. One of those will be time. Time is measured in hours in this problem. One of those will be the total distance. Which one is which? Hopefully you realize that the independent variable is time because we don't control time. Time passes on its own. Miles is our distance. Miles is our distance. So over here, I'm going to write for independent, I'm going to put hours. And for dependent, I'm going to put miles. And then we'll start filling in our table. If you struggle with that point, but you think you've got it now, I'd suggest pausing the video and filling in the table on your own. I'm just going to keep going. The independent variable, if 0 hours pass, the problem tells me they've already paddled 23 miles. But if another hour goes by, the current will have carried them 2 more. If another hour goes by, the current will carry them 2 more, and I can continue that until I have the entire table. Now, hopefully you've realized that this is a constant rate of change. We're growing by 2 miles every hour. And as we're filling in our table, we know that we always have those 23 miles no matter what else happens. The only thing that changes from one step to the next is how many sets of 2 miles we have. So if 0 hours have passed, we've not gone any sets of 2 miles. If 1 hour passes, we've gone the 23 and we've gone 1 extra set of 2 miles. And after 2 hours, it's 2 sets, 3 sets, 4 sets, 5 sets, so on and so forth. So if I wanted to know for any amount of time, notice the 2 never changes. That's our constant rate of growth. The time always matches, whoa, can I get that? There we go. Matches what's in our independent variable column. because it's 2 miles every hour, and that's counting our hours. But we always have that extra 23 giving us our function. Now you'll notice that I used g of x this time. G of x means the same as f of x. It's just a way of naming the function. So this is rule G. We also could have said it equals y instead if we had wanted. So if I were to ask you, how far will they have traveled after 2 days of drifting? We always rewrite the original formula or the original pattern. We're going to substitute in 2 days, which is time, and we're trying to find out distance. So we know the time, but the time is given to us in hours. So instead of putting in 2 days, I'm going to put in 48 hours. Those are the same thing. And then we just simplify, and they will have traveled 119 miles. Try this one. How long would it take them to travel the length of the Great Miami River, which is 170 miles long? In this question, I forgot my question mark, in this question, they're asking us about time, and they give us a distance. Well, we're going to do this the same way. We take our original pattern. We now know the distance, which is g of x. And we can use our single variable algebra skills to solve to find the time. How do I get rid of a plus 23? The property of equality says subtract 23 from both sides. And of course you would write that out, but I didn't because I'm running out of room here in the slideshow and you're already getting pretty good at this. To get rid of a times 2, we would use the property of equality and divide both sides by 2. And it would take them 73.5 miles. You see, once we know the pattern, the g of x equals 2x plus 23, there's all kinds of different problems that we can solve. I've got one more of these for you. Christoph and Sven have 2 tons of ice that they've brought back from the mountains. They deliver about 15 pounds at every stop. How much ice do they have left? Again, I'm going to suggest you try this on your own before watching me do it. I'm going to go ahead and assume you've done that, and I'm going to keep right on going. We have an independent and a dependent variable. The question is about how much ice they have left. How much ice they have left. Well, I don't know. It depends. It depends on what? Well, how many stops they make. So my independent variable is time measured in stops. My dependent variable is the amount of ice left. So this is the number of stops, and this is ice left. It's important for me to point out to you that time doesn't have to be standard increments of time like minutes, seconds, hours, or days. Time is any recurring event that we can use to calculate the change. Also, I should point out to you that we are counting or measuring or calculating the amount of ice left over, not the amount of ice that was delivered. Make sure your explanations are specific because those would result in very different problems. And then we'll fill in our table. If 0 deliveries have taken place or 0 stops, he has all 4,000 pounds of ice. Did you notice I switched that on you from tons to pounds? Make sure that you're consistent. A ton is 2,000 pounds, therefore he starts with 4,000 pounds of ice. After 1 stop, he's delivered 15, leaving us with 39.85, 39.70, 39.55, 39.40, 39.25. And hopefully at this point you've realized that this is a decrease of 15 pounds at every stop. Notice that's the rate of change that was given to us. It is important to point out that it is minus 15 every time because it is going down. Now, no matter what happens to the problem, we always started with 4,000 pounds. But the negative 15 tells us how each delivery or each stop affects or changes that 4,000. After 0 stops, there's no change. But after 1 stop, he's dropped off 15 pounds of ice. After 2 stops, he's dropped off 15 the first stop, 15 the second stop, so 2 sets of negative 15. So he's dropped off 30, 45, 60, and 75, meaning that I can use the information in this table to realize we're always going down by 15. The only thing that changes is how many stops we make. And we also notice that we started with 4,000 pounds no matter what else happens. That allows us to write this pattern. You'll notice this time I switched back to y. It really doesn't matter if we use y or f of x or g of x. They're all the same thing. So here is the relationship or the rule. Negative 15x plus 4,000 equals y. So if I asked you how long it would be before they run out of ice, you could try that on your own, and then you would watch me, and I would say, well, we start with our pattern, and we're asked to find time. Well, that's x. That means we need to know how much ice we have left. Well, this says we run out of ice. That means we have 0 pounds left. And now it's a single variable equation. How to get rid of plus 4,000? Subtraction. How to get rid of times negative 15? You divide, and you get 266 and 2/3. You get a little typo here. I had originally put in 1 ton, and I changed that, but I didn't change that extra slide. You'll also notice that this is a duplicate. So it comes out as 266 and 2/3. I got that by dividing both sides by negative 15. Hopefully that's been helpful for you and useful. Hopefully this is a pattern we can start to recognize. You should know that our goal eventually is to be able to generate this directly from the word problem without having to go through the trouble of making the table every time. It's important for us to recognize that this is always what we start with, this is always our rate of change, and that this is always whatever our increment of time is. You catch on to that, you'll be in good shape. For my students, I would expect, at least for now, that you would complete the entire table, and as we get better and better at this, we'll start to remove that requirement. Hopefully this has been useful. If it has, make sure you leave me a like. Make sure you ring that bell to turn on notifications. We're putting out new material all the time. Hopefully, if you're finding it valuable, you want to see that coming your way. As always, we do wish you the very, very best of luck. You guys take care of yourselves, okay? Bye-bye.